Hey guys, this video is to give you a little bit more practice with counting. So we're going to be doing this problem, which is similar to one that was posted on CampusWire, but just with a few more questions. And I'm going to be going through it part by part, so if you'd like to, you could pause the video, work on a question on your own, and then check your answers with mine. So let's get into it. We're going to be hosting a dinner party with 12 guests, and we're going to be counting different ways we can arrange 12 name cards around a circular table. And just to clarify, this is important, an arrangement only refers to who everyone is sitting next to. It doesn't matter which specific seat they're in. So if you have an arrangement of these 12 people around a circle, and then you shift everybody one chair to the right, it's still the same arrangement because everyone is next to the same two people. The first question asks us how many different ways we can arrange 12 people around a circle. So for argument's sake, let's think of arranging them in a line because we could place the two ends together and make it a circle. So for the first spot, we have 12 options, because anyone can go there. Then because we've already placed one, we have 11 options for the next seat, and so on. So we get 12 factorial ways that people can be arranged in a line. However, if we assign each person a letter, we can see that this up here is one of the 12 factorial arrangements. This down here is another one of the 12 factorial arrangements. And these are different arrangements within the line. However, we can see if we put the ends together and made these a circle, they are exactly the same because everyone has the same people to their left and to their right. There's actually 12 different ways that we can get the same arrangement. If you see in the first one, the A is in the first spot, and in the second, the A is in the second spot. And so this A can be shifted over 12 times. So we have to divide by that to account for all the circle rotations. Another way to think about it is if we set one person down at the table first, because it doesn't matter what seat they're in. And then we can just arrange the other people around it. So we'd have 11 options for the next person, 10, and so on. So we would get 11 factorial. And that gives us the exact same thing as 12 factorial divided by 12. So in seating n people around a table, the answer is n minus 1 factorial. Now we know that we can choose 3 people at the dinner party to receive one of 3 golden tickets. And we're trying to find how many different ways we can get these 3 people. We know that there can't be repeats because it says 3 different people. And we also know that order doesn't matter. Whoever gets the first golden ticket isn't any different than the person who gets the second golden ticket. And so we're essentially choosing a set of 3 from the 12 people. So for that, we can just use the formula for 12 choose 3. Now we're going to say that 6 of our guests are Democrats and the other 6 are Republicans, and we want to alternate them around this table. We can think of this similar to how we did the first question, and in that if we're arranging people around a table, we can stick one person in a specific chair to account for all the repeated arrangements. So let's say we can put a Democrat in this chair right here. And then for the seat next to them, it has to be a Republican. So we only have 6 options for who that could be. Then for the next seat, we have 5 options, because there's 5 Democrats left, because we've already set one down. And then 5 Republicans for the next seat, and so on. And I'm just going to fill the rest of these in really quick. And then because these are all independent choices that we can make, we can use the product rule to connect them all. Now, if we look at all the numbers that are being multiplied, we can get the formula 6 factorial for the Republicans and then 5 factorial Democrats. This could also be written as 6 factorial squared over 6. Now we want to give out our 3 golden tickets, but we want to make sure that they don't all go to 3 people of the same political party. In a previous part, we decided that there were 12 choose 3 different ways that you could give out the tickets to 3 different people. This counts all groups of 3 different people, including ones that are made up of 3 Democrats or 3 Republicans. So to get the answer to this question, we could find the total number of groups of 3 and then subtract off the ones that are 3 Republicans and the ones that are 3 Democrats. So our total number of groups of 3, and then the number of different ways we could make a group of 3 Republicans Well, we're choosing 3 different people out of 6 Republicans, and order doesn't matter. So it's 6 choose 3, and it's the same way for choosing the groups of 3 Democrats. And so if we simplify this, we have 12 choose 3 minus 2 times 6 choose 3. There's another way we could think about this problem, and that's how many ways we could make a group with 2 Democrats and 1 Republican, and how many ways we could make a group with 2 Republicans and 1 Democrat. So the number of ways we could choose 2 Democrats is just 6 choose 2, because we're choosing 2 different people out of a group of 6, and the order we pick them in doesn't matter. And the number of ways we can pick our 1 Republican is 6 choose 1, or just 6. And these 2 counts get multiplied together because they're both independent of each other. The number of ways we can count a group of 2 Republicans and 1 Democrat is written exactly the same. And now these 2 counts get added together because the total value we're looking for includes the number of groups with 2 Democrats and 1 Republican and the number of groups with 2 Republicans and 1 Democrat. If we simplify this out, it can be written as 2 times 6 choose 2 times 6 choose 1. And now both of these are valid ways to write your answer. If you wanted to get an actual number for your answer, you could expand this. So 12 choose 3 could be written as 12 factorial over 3 factorial, 9 factorial, then minus 2. And then for 6 choose 3, it would be 6 factorial over 3 factorial squared. And then the other answer would be written as 2 times 6 factorial over 2 factorial, 4 factorial, times 6 choose 1, which is just 6. If you calculate these, you'll find that they both give you 180, which is the number of different ways we could pick 3 people that don't all belong to the same political party. Now our 12 guests are 6 couples, and we want to count the number of different ways we can set our table so that all the couples are sitting together. To guarantee that every couple sits together, we could simply arrange the 6 couples in a circle instead of the 12 individual guests, imagining each of these lines as like a bench that seats 2 people. As we learned in the first part, the number of ways to arrange n people in a circle without any repeated arrangements is n minus 1 factorial. So to count the number of ways we could arrange our 6 couples in a circle, we would get 6 minus 1 factorial. Now that we have all the orders of couples, we have to count the orders within the couples. Again, if we were to give every guest a letter, this couple up here could be seated like this, or they could be seated like this. So there's 2 different ways we could order this couple, 2 ways for that couple, 2 different orders for all the couples, which gives us 2 raised to the 6th power. Now the total number of ways we can set our table is 5 factorial for the order of the couples times 2 to the 6th for the order within the couples. Now we're using the product rule to multiply these 2 counts together because the arrangement of couples in a circle is independent from the order within these couples. So for every 5 factorial way we can arrange the couples in a circle, there are 2 to the 6 ways we can switch up the order of the people in the couples while keeping them together. For this question, when we place down our 3 golden tickets, we have to make sure that no couple gets 2 tickets. In other words, the 3 tickets have to go to 3 people that are all in different couples. To guarantee this, we could first choose which 3 couples win a ticket, and then choose which person in each couple actually had the ticket under their plate. Now, how can we count this? To count the number of ways that we could choose 3 different couples is just 6 choose 3, because order doesn't matter, and all of the couples have to be different. Now for each couple, we have 2 choices for which person actually got the ticket, which gives us 2 raised to the 3rd power because we're dealing with 3 couples. Let's say that these are the 3 couples that were chosen, and this is just 1 out of 6 choose 3 options. Couple 1 is made up of A and B, couple 2 is made up of people C and D, etc. So for this specific group of 3 couples, there are 2 to the 3rd or 8 different ways you could choose the actual people who got the ticket. You could choose like A from couple 1, C from couple 2, and E from couple 3, and so on. And so this is why we multiply 6 choose 3 by 2 to the 3rd, because for every way you could choose a group of 3 couples, there is 8 ways you could choose the 3 individual people who actually get the tickets. So the answer for this part is 6 choose 3 times 2 to the 3rd. all the answers to the questions that we've done so far. There is still one question left, but I'm actually going to solve this one in a part 2 video because it is a pretty tough problem and I don't want to make this video too long so that nobody watches it. However, if you're really curious about the answer, I think one person has solved it correctly on the Campus Fire post, so you can go check that out.